Lesson 6.5, Arithmetic Sequences. This lesson might seem a bit unrelated to the other lessons we've done in this chapter, but I promise it's related. To recap, linear growth is just when we're growing by the same amount each time. We've talked about linear growth a whole bunch in this class so far. In this lesson, we're going to apply what we know about linear growth to a type of pattern called arithmetic sequences. Note that this word here is the same as arithmetic. It's spelt the same, but in this situation, we pronounce it arithmetic. It's an arithmetic sequence. We have some new vocabulary. First is a sequence. This is just a list of numbers. So example 2, 4, 6, 8, or 1, 2, 3, 4, just a list of numbers. A term is a number in a sequence. So 2 is a term, 4 is a term, etc. And it's represented by T and with a subscript N. So T is for term and N is the term number. So in this example here, T1 is equal to 2. The first term is 2. And T2 is equal to 4. The second term is 4. We're going to focus on arithmetic sequences. This is a type of sequence where the difference between each term is always the same number. So example 3, 6, 9, 12. That's going up by 3 each time, so it's an arithmetic sequence. Same with this one, 2, 4, 6, 8. It's going up by the same amount each time. You could have a sequence where it's not arithmetic. If we had 1, 4, 10, -6. That's just a random list of numbers. It's still a sequence, but it's not changing by the same amount. So it's not arithmetic. We're not going to talk about that today. Lastly, we have the common difference. This is how much an arithmetic sequence goes up by each time. And it's represented by the letter D for difference. So in this example here, the common difference is 3. D is equal to 3. It's going up by 3 each time. Let's look at some examples. First one, for each arithmetic sequence, identify the common difference. So we've got 3, 5, 7, 9. That's going up by 2 each time. So the common difference, or D, is equal to 2. Next, we've got 11, 8, 5, 2. This is going down by 3 each time. So our common difference is equal to -3. Make sure you don't forget the negative. Your common difference can be positive or negative. An arithmetic sequence just has to be changing by the same amount each time. Just make sure you include the correct sign if it's going up or if it's going down. Next, are the following sequences arithmetic? Explain how you know. Okay, well, this first one, we went down by 4, but then we went down by 6. So this is not changing by a consistent amount. It is not an arithmetic sequence. That's just a regular sequence. And the next example, -1, -4, -10. It's going down by 3 each time. It's a consistent amount, so yes, it's arithmetic. The common difference is -3. So now that we know this vocabulary, let's try to build a general formula for arithmetic sequences. We can use this example here for it. So the sequence is 3, 7, 11, 15. This is going up by 4 each time. So the first term, T1, is 3. The second term, T2, well, it's 7, but we can write this as 3 plus 4 because the common difference is 4. So we just took whatever we had before and we added 4 to it. The third term, T3, well, it's going to be equal to the first term plus 4 plus another 4. In other words, it's equal to 11. But how did we get there? By adding the common difference 2 times. And then the fourth term, T4, well, it's equal to the first one plus 4 plus 4 plus 4. So we can see that a pattern is emerging here. We always have 3. The first term is always here. And then we're adding the common difference a certain number of times. We can probably assume that for T5, it's going to be 3 plus 4 plus 4 plus 4 plus just one more 4. So we can turn this into a general formula. For T2, instead of writing it as 3 plus 4, we can write it as 3 plus D because we already identified that D is equal to 4. Okay, so the second term can be represented by 3 plus D. The third term, again, let's replace 4 with D here. So we've got 3 plus D plus D. And since we have 2 of the same variable, we can write it as 2D. We can repeat this process for the fourth term. We replace all the 4s with D. We have 3 of them in total, so we can write that as 3D. So what do we notice? Notice that the coefficient in front of D is always 1 less than the term number. So for this term 4, the coefficient in front of D is 3. It's 1 less. When we have term 3, the coefficient in front of D is 2. It's 1 less. And the same is true here. For the second term, we just have an invisible 1 coefficient here. It's 1 less. So we can use this to build our formula right here. Any arithmetic sequence can use this formula to find any term in the sequence. What are all these things equal to? Well, we know that Tn, this is just a term. So the nth term, whatever number you want to sub in for n, that's fine. You can find any term in the sequence. If you want to sub in n equals 100, you can find the 100th term. A is equal to the first term in the sequence. N is equal to just the term number. So again, the 100th term or the second term. We have this -1 here because remember we just noticed that it's the relationship between these two numbers is that this one's always 1 less. And then lastly, we've got D that represents the common difference. So this general formula is really useful because you can find any term in the sequence, even if it's really far away. So for this sequence here, we only have the first 4 terms. If I wanted you to find the 500th term, you're going to be here all day if you're slowly writing out every single term up to the 500th one, just adding 4 each time. Instead, you can do it a lot simpler using this formula. So let's look at some examples. Find the 12th term of the arithmetic sequence 2, 5, 8, ... That just means it goes on forever. So first we can write down what we know. Well, A represents the first term. The first term here is 2. D is the common difference. These are going up by 3 each time, so D equals 3. And we're looking for the 12th term. So that means that my n is equal to 12. Then I take my general formula right here, and I plug in what I know. Well, I'm looking for the 12th term, so I can just replace this n with 12, but this is what I'm looking for. Replace A with 2, n with 12, and D with 3. Then I can calculate. So that gives me 11. Multiply those, I get 33. Overall, I get 35. So therefore, the 12th term is 35. What other type of questions could you be asked? This one's kind of like the opposite. Which term in this sequence has a value of 439? So we want to know we have the value and we want to find n. We don't know what term number that's for. So we write down what we know. The first term is 4. The common difference is 3. It's going up by 3 each time. We don't know our n, but we know that that term far out there is 439. We need to find our n. We write out the formula and we plug in what we know. We know that the term is equal to 439. We know our A, we know our D, but we don't know our n, so that's our blank. We will have to solve for n. It takes a couple more steps than the last one. So we have to get it on its own. First, why don't we just minus 4 on both sides so that this can be by itself, one step closer. We minus 4 over here, we're left with 435. Okay, now we can divide both sides by 3, trying to get that n on its own. 435 divided by 3 is 145. Lastly, we just have to add 1 to both sides to get n by itself. So we get n is equal to 146. So we just found that the 146th term has a value of 439. That's a pretty far away term. There's no way you're going to sit here and count each one. That's why this formula is useful. The last one is a trickier question, and it uses what we've done so far in this chapter. The 7th term of an arithmetic sequence is 78, and the 18th term is 45. Find the first term. So we don't actually have that much information. We don't know A, we don't know the first term. We also don't know D. We have no idea how much this is going up or down. All we know is this. The 7th term is 78, the 18th term is 45. So we don't know what to do yet, but let's just start with our formula and plug in what we know. First, I'll do it for the 7th term. So T7, okay, I don't know my A. I know my N, I don't know my D. So I can simplify that to give me 6. And I can plug in, I know that T7 is equal to 78. So this is what I'm left with. It's not super useful yet because I still have 2 unknown variables, but we'll see what else we can do here. Repeat the process with the 18th term, plugging in what we know. Same thing, this is not that useful because my A and my D are still unknown. So we look at this, we have two equations, they have two variables, and these are linear equations. We actually do know how to solve this. We can use our systems of linear equations, just like we've been doing so far in this chapter. So I used elimination to solve. I put these two equations on top of each other. I didn't even have to change them because the A's are already identical, so I can eliminate right away. Using elimination, I found that the common difference is -3. So I'm almost there. I need to find the first term. So that's what I'll finish with here. If I know D is equal to -3, I can just take either one of the original equations, replace D with -3, and solve. So after all that, I get A is equal to 96. So therefore, the first term of the equation is 96. So hopefully now you can see the relationship between what we've just learned and what we've been doing so far in this chapter.